In this short video, I'm going to talk about the properties of liquids. The first property I want to talk about is viscosity, or resistance to flow, or which you can also think of as goopiness. High viscosity is due to resistance on individual molecules moving around in a liquid. Going back to the first slide in this chapter, I said that the phase in which a substance exists depends on the relative extents of its intermolecular forces and kinetic energies, which are directly related to temperature. You can think of high viscosity as a liquid becoming more like a solid. So, an increase in intermolecular forces and a decrease in temperature will make a liquid more goopy. To repeat, high viscosity is due to strong intermolecular forces in the liquid, and viscosity increases as temperature decreases. When looking at chemical structures and thinking about viscosity, small molecules are generally low viscosity. So here I'm showing water, mercury, and methanol. In terms of larger molecules, nonpolar molecules are going to have weaker intermolecular forces. And so, with all other factors equal, the more nonpolar molecule is going to have the lowest viscosity. Here I'm comparing two similar nonpolar molecules that consist of nothing but carbon and hydrogen chained together. When comparing these two, the smaller molecule is the one that has the lower viscosity. Here I'm comparing a molecule with many hydrogen bond donor-acceptor groups to a molecule with only one hydrogen bond donor-acceptor group. This molecule is also larger, and this molecule is smaller. So if I were to compare this molecule here, which is a sugar, to this molecule here, ethanol, the larger molecule with more intermolecular forces is going to have the higher viscosity. Another unique property of liquids is surface tension. Surface tension is the resistance of a liquid to spread out and increase its surface area due to it being attracted to itself more than air. In general, matter likes to spread out, increase its disorder over time. Surface tension stops the spreading, as we see with these beads on this leaf. A molecule in what we call the bulk is in contrast to the surface. A molecule in the bulk is lower in energy than one at the surface due to more cohesive interactions, which lower energy. To illustrate this, we see a molecule of water here is forming 6 cohesive interactions with other water molecules around it. These are, of course, hydrogen bonds. This molecule on the surface is only able to form 4 cohesive interactions. The more interactions a molecule can make in general, the more stable it is, the lower in energy it is. By analogy, a molecule of water in vacuum is at a higher energy than one in the middle of liquid water, because it is unable to form stabilizing interactions with other matter around it. Similarly, this water on the surface forms fewer stabilizing interactions because it cannot interact with air, which is made of a low density of nonpolar molecules. Instead, the lowest energy state of water involves formation of one molecule thick layer of ice on the surface. This ice layer gives water a thick skin that is able to support insects on the surface and causes water to bead up on this waxy leaf, which has a nonpolar coating on it. So water does not wet or adhere to air or other nonpolar substances like wax that we find on that leaf. But water does wet polar materials like paper or fabric or glass. Here we see 2 capillaries. The one on the left contains mercury, the one on the right contains water. We see here that polar water rises up the sides of a polar glass tube because it can form adhesive interactions with the glass. It rises as long as adhesive forces are stronger than cohesive forces. Adhesive forces are the forces between liquid and another substance, and cohesive forces, like I mentioned on the last slide, are the ones holding water together. The water will try to spread out along the surface of the tube and reaches an equilibrium when the weight of the water beneath it, pulled by gravity, draws it down. Water in the middle here does not rise up because it has nothing to adhere to. In contrast, nonpolar mercury rises in the middle of the glass tube because it wants to spread out and wet the nonpolar air above it, and is unable to wet or adhere to the glass itself because the glass is polar. So here the cohesive forces on the edges are stronger than the adhesive forces, and the mercury in contact with the tube does not spread out and rise along it. The last property of liquids that we'll look at is capillary action. And capillary action is simply liquid trying to minimize the effective surface tension. When liquid molecules are strongly attracted to the tube molecules, the liquid creeps up the inside of the tube until the weight of the liquid and the adhesive forces are in balance. The smaller the diameter of the tube is, the higher the liquid can climb, because there's less water bulk in the middle pulling it back down. This phenomenon is of course also temperature dependent, because molecules at higher temperature have more kinetic energy to counteract the attractive forces holding them together. Here I'm showing you an equation that you'll never actually have to apply, but I'm showing you this equation because it describes what variables determine the height of capillary action. Here we see a temperature dependence. The height is higher, the higher the temperature. We see an angle dependence. The lower the angle of the capillary, the more it will rise because there's less gravity to fight against. We also see dependence on the radius of the tube. A smaller radius leads to a larger height. We see the density is involved. Lower density leads to greater height. And we see that gravity is the force that counteracts everything, so that the gravitational constant g is involved. And this is it for our exploration of the properties of liquids. Next, we're going to move on to solids.